All right. So we introduced Gauss's law. And today we want to talk about some applications of Gauss's law. Gauss's law. So Gauss's law can be stated, Gauss's law is part of the postulates of electrostatics. And there were two postulates. Postulate one. Postulate means something, of course, postulate means something that's given a priori without any proof, assumed to be, something that's a fact of nature, and we derive everything from it. So there is the Gauss's law, which can be expressed in both a microform, infinitesimal form, meaning if you zoom in into a really tiny volume, or it can expressed in a macro form, meaning you integrate over an area, over a volume. So in microstate or differential form, it is the divergence of E is rho over epsilon naught if it's air. And then if you integrate this using the divergence theorem, you get that a surface integral along any closed surface, the flux along any closed surface is just going to equal the total enclosed charge over epsilon naught. So this is Gauss's law. And then there's postulate number two about the curl, which states that the curl of E equals 0, and the circulation of E, this is L, E dot L equals 0. The circulation along any closed path is 0. So we've proven this. We've also, I think, we can, I'm not sure if we've proven this, but we can discuss this. But as far as Gauss's law is concerned, Gauss's law gives us a new method now for calculating the electrical field. Because previously, the only method we had for calculating the electrical field is to take any charge distribution and deviate up into small segments, small components. And each component can be treated as a point. And then we calculate the field for every point using Coulomb's law, and then we sum everything up to get the total field. Okay. Of course, E1, E2, E3, whatever. Okay, so this is the only method we have to calculate the electrical field. But then Gauss's law given here opens up a new method for us, which is directly using Gauss's law, right? If I know that the flux is going to equal Q enclosed, I can use this to calculate Gauss's law. Is this now simpler than using Coulomb's law directly? That's debatable. That depends on the problem. Usually when you have problems with high degrees of symmetry, if you have a problem with a high degree of symmetry, then it's easier to use Gauss's law. One example is, the simplest example we can think of is a point charge. Let's say you don't know Coulomb's law. Here, I'm giving you this as postulates. That's the idea. So the idea is that forget about Coulomb's law. Those are the postulates of electrostatics, essentially. So we started with Coulomb's law, and then we got the postulates of electrostatics, but we can do the reverse. We can start with those two as postulates, and then we can go back and derive Coulomb's law. And this is the common picture, actually. This is the way people treat this, is that they, although Coulomb's law leads to those two equations, we consider those two equations as more fundamental. The point is that Coulomb's law only deals with electrostatics. Those laws are more general, most general, because they deal with everything. Those are true whether the charges are moving or not. Coulomb's law is not true if the charges are moving. So that's the big difference. So we consider those more fundamental. So let's say we have a point charge Q. What we can do is we can use the spherical symmetry, and we can assume our surface. So we enclose the charge with the surface, a distance r, a spherical shell. Okay, And then we know Gauss's law tells us the flux of E coming out of that surface, right, equals Q enclosed, which is Q over epsilon naught. Right? This is what Gauss's law tells us. And we can derive Coulomb's law from that. And how do we derive Coulomb's law from that? Again, this is a problem that has a lot of symmetry. Right? Would it make sense in this case for the electrical field to be variable depending on where you are on the sphere? No, it wouldn't, right? Because the problem is symmetrical. From whatever direction you look at the sphere, it looks the same. Nature doesn't know what angle you're looking at the sphere, right? So
as long as it's symmetrical.
Yeah, as long as it's symmetrical, the E should be equal anywhere on the sphere. Furthermore, it should be pointing away. Right? Because again, if you have at one point E is at some angle, that shows you that tells you that nature has a preference for a certain angle. Nature has that's the key point here. It's a subtle point, but the key is that nature has no preference for a certain direction. Everything, all directions are equivalent as far as it's concerned. So this is kind of like this is something where ultimately shows up in many forms in this subject, and ultimately leads to relativity. I mean, electromagnetism is a fully compatible with the relativistic point of view, where nature does not care about where you are, what speed you're going. It is symmetrical. Okay, so using that, we can consider E to be constant at the sphere. We can take it out of the integral, right? So if we take E, so if we rewrite this as some ER, and then what can I write this as the unit vector? Let's take spherical coordinates, right? System. ER is constant along a constant R. So this is going to become ER R dot ds Q over epsilon naught. ER, this is the component, the radial component of the electrical field. This has unity, right? So this is going to be ds magnitude, right? The angle, what is the angle between R hat and ds? This is a surface element. Surface element is pointing in this direction, so they have the same direction. So the cosine between them is 1, right? Cosine 0 is 1, right? So this is essentially, this integral is essentially the area of the sphere. What is the area of the sphere? 4 pi r squared. This is why we put in that pesky 4 pi in Coulomb's law, because we derive Coulomb's law. We want to derive Coulomb's law from this. All artificial, right? It depends on your point of view. Right? So ER is going to be Q over 4 pi epsilon naught r squared, and this is Coulomb's law. Okay, so this is the simplest problem with symmetry. There's another, and we can apply this also to charge distributions with symmetry. So this does not only apply to point charges. We could apply this to charge distributions with symmetry. For example, a line, an infinite line. This is a symmetrical problem, right? It has axial, it has cylindrical symmetry. So unlike a point where it has spherical symmetry, meaning I can look at the point from any direction and it's going to be fully symmetrical. Here I lose some of the symmetry, but there's still a high degree of symmetry, because if I have a line, I can rotate along the line, and the problem is still going to be symmetrical. But again, the key thing here is I want to apply Gauss's law, and to apply, I want to apply Gauss's law in a way where I don't have to really do this integral. You always want to try to avoid doing integration. That's the point of Gauss's law. Gauss's law shows up in integral form, but the point is not to do the integral. The point is that to recognize that this integral will be the same for any surface that you choose. So you have to choose a surface. Choose a surface that makes this integral the simplest calculation possible, right? So here I could, if I'm stupid, I could choose this surface, something like looks like a potato, right? But I don't need to do that. I need to I can choose a cylinder that's centered along the line, right? Right. Okay, cylinder centered around the line, right? And this has rho L here, right? Rho L. Okay, and assume it's a uniform charge distribution. So let's say this length here is L. Length of the cylinder is L. An arbitrary cylinder. Length L could be anything, right? And now I can use Gauss's law. Now I can say E dot ds equals Q enclosed. What's Q enclosed? It's rho L times L. That's the total charge enclosed within the surface. Here from the symmetry, I know that the field coming out of the cylinder, ER, let's call it E small r hat. I'm using cylindrical coordinates now. Is going to be, due to symmetry, has to be equal everywhere on the cylinder. Furthermore, on the sides, it will be perpendicular to ds. It will be perpendicular to the surface, vector representing the surface. So whatever dot product here is always going to be 0, right? Cosine pi over 2 is 0, right? So the sides of the cylinder won't matter. So here I can write this as ER, which is a constant. I can take it out of the integral. This is over the cylinder. What r hat dot ds. And this is only this side of the cylinder. I ignore this, the top and bottom of the cylinder because the surface elements have a direction that's always perpendicular to the field, to ER. So they don't contribute anything. Okay. What is then the surface area of the cylinder here, ignoring the top and the bottom? So it's the length of the base times the length, right? What's the length of the base? It's 2 pi. Let's call the cylinder has a radius small r. Okay, so this is going to be 2 pi r. That's the circumference of the base of the cylinder times L. Notice L cancels with L, and we end up with ER equals rho L. Oh, I forgot the epsilon naught here. Rho L over 2 pi epsilon naught R. And this is exactly the result that we got using Coulomb's law, right? Remember when we previously, when we did this calculation by direct integration, I think we did it last time. Oh, last time we were talking about the cloud, cylindrical cloud, but we did it. Oh, so here we did it. If we assumed we started with a finite line and then we extended the line to infinity, and we got 2 pi epsilon naught A. A was the distance we are from the line. So we got exactly the same result. We got exactly the same result. By the way, making the line, what's the point of making the line infinite? The point of making the line infinite is to make the problem symmetrical. Because if the line was not infinite, the fields around the center will be radial, but the fields around the edges will look something like this. Okay? It turns the problem into a problem that's not symmetrical. That's harder to calculate. That forces you to do the integral. However, making the line infinite makes our fields nice and symmetrical, makes our field all pointing outwards radially from the line. Right? Because now the problem became symmetrical, the integral becomes easy to calculate. If you do a problem, if you try to find a field using Gauss's law, and you discover you have to do some integration, you're doing it wrong. You probably should go back. If you cannot find a symmetrical surface, then you should probably go back to the Newton method. Not the Newton method, sorry, the Coulomb method. Okay, the other symmetrical problem that we calculated, and let me see, I think I have, we did that also. We did a surface. Did we do a surface? We did like a surface, but we did not, we found the field on the surface itself. We did not calculate the field like away from the surface, probably because it was a bit of a difficult integration. So let's do an infinite surface. So let's say you have a surface and it's infinite, it extends everywhere. And it has a surface charge density, rho s. So again, you have to find the Gaussian, what's called the Gaussian surface. The Gaussian surface. So here, what would the field look like? The field will always be radial, right? So it's gonna, we want to find the field, the distance, I don't know, let's call it A, distance A from the surface. So the field is gonna be radial. It's gonna be something like this, let's say. It's gonna be the same everywhere, and it's gonna be pointing away from the surface. If I go under the surface, the field is going to be pointing this way. Excuse me. Okay. So let's say the field is, so I need to find a Gaussian surface. The Gaussian surface I could find, the simplest I could think of is something like this. Any surface really with any area, let's call this area A. Could be anything. I could have drawn a cylinder, but I don't need to make it that symmetrical. But then the surface extends to under the sheet. So this is a sheet, infinite sheet. So it's a surface that looks like this. It has a side that's above the sheet, a side that's below the sheet, and then it intersects the sheet. From the symmetry, the sides of this surface, closed surface, will not contribute anything to the Gaussian integral. Why? Because the surface elements are always going to be perpendicular to the electrical field. Only the top and the bottom is going to contribute. Okay, and assume this has distance A here, and this has distance A too. Okay. So what would be, so using Gauss's law, what does Gauss's law say? E dot ds equals Q enclosed. Q enclosed is rho s times A. So this intersection here gives me a surface on the sheet. The charge enclosed in this volume is going to be rho s times A. Okay. Now I can divide this into two parts, the top flux and the bottom flux. The top corresponding to the top section of this volume surface, and the bottom section of this surface. So this is going to be a top, and this is EZ, I guess, Z hat dot ds plus EZ A bottom Z hat dot minus Z hat dot ds, right? Because on the bottom, I'm the field is going to be pointing in the opposite direction. The field is pointing in the direction of minus Z hat. Here I'm using a Cartesian coordinate system. So this equals rho s A And this is not the same EZ. This is EZ at this is EZ at A. This is EZ at minus A. Okay. So the key thing here, from the symmetry of the problem, let me see. I don't want this to end up being zero, actually. I don't want this to be end up being zero at all. So this should give me some value. So yeah, so this is right. So E is just going to be the Z component at that point at A, Z hat dot ds, assuming this is equal to this from symmetry, and at least in magnitude, right? This is going to be 0. All right, let me. Oh, ds. So this is negative, but ds is also so ds here is pointing in this direction. ds in the bottom is pointing in the opposite direction. So this cancels the negative sign, right? This essentially cancels the negative sign. So essentially what we end up with is this is A, right? And this turns out to be A because I'm integrating over the surface area. So I end up with 2A EZ equals rho S at A, of course. A cancels with A. And it's very simply, EZ at A is going to be rho S over 2. Is that what the yeah, very interesting result. Why is it very, of course, we forgot here the epsilon naught. This is a very interesting result. If you have an infinite sheet, the field, a distance A away from the shield, notice first it does not depend on the distance, right? It does not depend, it's really constant everywhere. So whether you are 1 meter from the sheet, infinite sheet, or 1 million light years from the infinite sheet, the field is going to be exactly the same. This is a really interesting result, and this is again also a manifestation of symmetry. If you have an infinite sheet, right, whether you're 1 meter away from the sheet or 1 million light years away from the sheet, does it matter? The sheet will always look the same to you, right, because it's infinite, right? While if it's a finite sheet, the further away you go, the sheet is going to turn into a point. But because it's an infinite sheet, it doesn't matter whatsoever how far you are from the sheet. The field is always going to be rho S over 2 epsilon naught. Okay, why is this useful? Because many applications, an infinite sheet is a good approximation. That's why when you look at capacitors, capacitors are designed to have a large area, right, with a small distance between them. So this kind of like allows you to kind of approximate the sheets of the capacitor as infinite sheets. Because inside the capacitor, between the two sheets of the capacitor, conductors, that might as well be infinite because the two sheets are really close to each other, but the area is large compared to the distance. Of course, capacitors are not sheets. Capacitors are kind of like really sheets, but it's a little bit more intricate. So sheets that are rolled like like a Swiss roll cake. Swiss roll cake. So it's like two sheets that are rolled like a cake, like a Swiss roll cake, and that's how you get like a humongous surface area. But this would be like a good approximation for the field across any of the sheets. Okay. So there's an example. Okay, so there's an example of the book, example 4.2. And this is an application of a spherical charge distribution. So let's state what the problem. State the problem. So two very thin spherical conducting shells are charged as in figure 4.4a. 4.4a shows you that you have from the origin a distance a, you have shell number 1, right? And this shell has a charge minus q. And then distance b from the origin, you have a second shell, spherical shell, and this has charge q. Of course, r radially could vary. R could be like inside, and r could be in between those two shells. Here I'm drawing the Gaussian surfaces, right? And then I could be outside. R could be here. So I want to calculate the electrical field everywhere. And I can use Gauss's law to do that, right? So this is the point of Gauss's law. What's the field inside? You know, previously, if you looked at this problem, you would, oh, I have to integrate or figure out the symmetry or whatever, and blah, blah, blah. Even you don't even have to figure out the symmetry inside the two shells. From Gauss's law, the field has to be 0. Right? Because this problem is symmetrical, of course. If the problem is not symmetrical, that wouldn't be true. But because this problem is symmetrical, the field inside has to be 0, because Q enclosed is 0. So if you are inside those two shells, E dot D ds equals 0. Q enclosed is 0. And because of the symmetry, I can take E out. So this is going to be ER r hat dot ds. This is going to be 2 pi r, right, squared. Doesn't matter. ER is still going to be 0. So the field, if you plot the field, ER, from 0 to A, the field is going to be absolutely 0. Okay. Now, what about the field from A to B? From R equals A, so this is R less than A. What about if R larger than A and less than B? Okay, Q enclosed is what? Is minus Q, right? Minus Q. And then Gauss's law, ER r hat dot ds. Again, this is, I can take this ER out as a constant because the problem is symmetrical. It has spherical symmetry. I should call this E capital R to spherical coordinates. So it's going to be ER minus Q yeah, minus Q over 4 pi epsilon naught of, I always forget the epsilon naught for some reason, r squared. Okay, this is 4 pi r squared. Just take it to the other side. Okay, so what would the field now look like? Well, there's now a sudden discontinuity. What is the field? Once I cross A, I see the minus Q. So suddenly my field turns into this. So there's a discontinuity in the field. What is the field at that point? Instead of R, put A. So it's going to be, the field's going to jump to minus Q over 4 pi epsilon naught A squared. Okay, it's going to keep increasing. Well, as R increases, is going to keep decreasing in magnitude, but it's negative, so it's going to go up, right? Get closer to zero, essentially. Until we hit B. At B, we're going to reach minus Q over 4 pi epsilon naught B squared. Okay, and then what happens when R gets larger than B? What's Q enclosed? Q enclosed is going to be minus Q plus Q. So it's going to be 0 again. ER 2 pi R squared. I'm not even writing the integral. I'm writing it as ER times the surface of the Gaussian, the area of the Gaussian surface. So ER is going to be 0. So the field is going to jump again down to 0. Collapse back to 0. Okay. Oh, okay. The example also does what happens if you swap Q plus and Q minus. You get the same thing, but it's going to be inverted. So you'll get this instead of that. That's the only difference. Okay. So that's Gauss's law. You can also use Gauss's law to calculate equivalent charges. That's another application. So you can calculate, let's say you have a problem so typically how we calculate, you might have a problem where you know the field, but you don't know the charges enclosed within in a certain volume. So Gauss's law would be a way to calculate the total charge enclosed in a surface. So, for example, this is an interesting example. So application. What's the when trying to find the electrical field intensity and charge density in and around a thundercloud. So we have a spherical cloud. Of course, the approximations are always interesting. Spherical cloud. We've all seen those. Charged particles of radius R0 equals 1 meter. Produces a non-electrical field intensity inside the cloud. So for R less than R0, let's say the field is known. Someone gives you the field. Hey, someone went into the cloud in an airplane and measured the field everywhere. And it turns out E equals R hat R squared. They discovered this is the Newton over Coulomb. Right? So the question is, knowing the field, can we know the total charge in the cloud? And the charge density in cloud. Not only the total charge, but also the charge density. How is the charge distributed in the cloud? Because we have the field at every point in the cloud, yes, we can do that. So the total charge is easy. Total charge is easy from Gauss's law. E dot ds equals Q enclosed. So assume that the Gaussian surface is right at the edge of the cloud. Okay. So what is the field there? The field, so this is going to be ER from symmetry, right? And then the surface area of the Gaussian surface, which is 4 pi R naught squared. And what is ER there? ER there is E is R hat R squared, right? So the magnitude is going to be R naught squared, right? ER is going to be R naught squared. So it's going to be 4 pi R naught to the power 4 Q total over epsilon naught. So Q total is simply 4 pi epsilon naught R naught to the power 4. Did I do this right? I think I did this right. I think the book has a typo. The book says 4 pi R naught squared epsilon naught R naught squared. He says that that equals 4 pi epsilon naught. So that's clearly a typo. There are typos in this book. But I have the 3rd edition, maybe newer editions. Most of you probably got the PDF. Okay. Shouldn't say the quiet part out loud. But I'm going to edit this and erase that. But yeah, so the book has a typo. Oh, no. No, not a typo. Sorry. I misjudged the guy. Sorry. We know that R squared, R naught is equals 1 meter. So if you plug that in, yeah, then Q total equals 4 pi epsilon naught. Yeah, that's absolutely true if R naught equals 1. Okay, what is the charge distribution in this case? There are 2 ways actually to calculate the charge distribution. One way is to assume that the essentially the easiest way to calculate the book goes through 2 ways methods. It's really the same, but one is more complicated than the other. So it goes through assuming like a arbitrary Gaussian surface, and then knowing that the total charge enclosed inside the surface is going to be rho v dv. So this is over that volume, and that's going to equal E dot ds, right? And E dot ds you can calculate. Yeah, he does some weird method through integration. Through integrating no, he doesn't even use Gauss's law. He just integrates the volume charge density, right? And he notes that the volume charge density is a function of R. This is an assumption, right? And then you can divide this into its surface element, volume elements, right? And because rho v does not depend on R, you can integrate over phi and theta, and you get an equation for the integral. Okay. So he does it through this integration, a simpler way actually, which I prefer. So you can go through it, but the simpler way is just to go back to the postulate. Go back to the microscopic form of Gauss's law, because E is already given to you. So divergence of E equals rho over epsilon. So the postulate gives you the microscopic form of the postulate, gives you rho directly, rho V. So all you have to do is you have to calculate the divergence of E. E is given in what? E is given in spherical coordinates. So I just have to go back and use the divergence formula and spherical coordinates. What's the divergence of E and spherical coordinates? It's 1 over R squared delta R squared ER over delta R, right? And the rest is going to be 0 because the field does not depend on theta. The field does not depend on phi. The field is symmetrical. Wherever you look at it, it only depends on R. So the rest is going to be 0, right? So this is going to be 1 over R squared. What's ER? ER in this case is R squared. So this is going to be r to the power 4 delta r to the power 4 over delta r. So this is going to be 1 over r squared, 4 r to the power 3 right? So this is going to be 4r, right? And this should equal rho v over epsilon naught. So rho v is 4 epsilon naught r. This is the charge distribution in space. Notice it starts at 0 and then it starts increasing linearly with r. That produces this sort of field. Okay. So we have now two methods to solve for the electrostatic field. We have direct application of Coulomb's law using superposition. We have the Gaussian way of doing it using the postulate. But then the second, we can now use the second postulate and introduce what's called the electrical potential. Remember, the second postulate was that curl E is 0 and circulation of E dl is 0. Those postulates always come in pairs. They come in the microscopic form, differential form, and the macro form, integral form, global form. So infinitesimal and global versions of the law. Okay. And although we proved Gauss's law conceptually, here we can also prove this conceptually by noting that if I have an electrical charge for a point, right, the field is going to always be radial, right? So if I take a curve, closed curve, that lies on the radius of this circle, of the sphere, the field is always going to be pointing out 90 degrees from this with respect to this curve. So the circulation is always going to be 0. Right? But now the key here, similar to what we discussed conceptually for Gauss's law, if we contort in Gauss's law, we contorted the area, and we convince ourselves that the flux will be the same. In the same way here, we could, in a small region, contort the curve a little bit. So in this, if we zoom out, the curve is coming this way, the field is pointing out in this direction. If we can contort the field a little bit, like this, the curve a little bit like this, we will get the same circulation, essentially. So we can infinitesimally contort this so that we reach the result that for a point charge, after applying an infinite amount of contortions, we will get like some arbitrary curve, right? So we can show that this curve is going to have the same value as this curve. So it really doesn't matter what curve you are integrating; you're always going to be the same value, and it's always going to be 0. So any closed curve around the point charge is going to be 0. Now, how do you complete the picture and get the postulate? You apply superposition. Superposition says that even if I have a charge that's not a point charge, so I've proven this conceptually at least for a point charge. Even if I don't have a point charge, I can I can use superposition. I can say any point charge, any discharge distribution problem can be considered to be a problem with point charges, and then we sum up the results together, right? So using superposition, I can divide any charge distribution into point charges. And this is true for every point, so this is going to be true for the total. How does this postulate introduce the electrical potential? Well, this is a rotational field, and we said that any rotational field, any field where the curl is 0, can be written. So remember when we discussed Helmholtz theorem, if this is 0, that means E can be written as the gradient of some scalar field, meaning a field that's a value at every point in space, not a directional field. The scalar field we call V, and this we call the voltage. Essentially, this is just mathematics. Because the field is rotational, I can write E as a gradient of some scalar field V. And this scalar field V, we call the voltage. If this is not true, if curl E is not true, then the voltage does not exist. Okay? And actually, the voltage only exists, electrical voltage only, or potential only exists in electrostatics. It does not exist in general, because in general, if you have dynamics, if you have charges that are moving, curl E turns out it's not going to be 0. It's going to be equal to the current, okay, magnetic current. But for now, in electrostatics, the curl E is 0. So, okay, so we're going to discuss the electrical potential next time. And yeah, okay, so any questions before we leave?